Hello! Today we are going to present the Locality of Different Program SWM for Subject Computer Organization and Architecture. We are the group number 7 and this is our team members, which is me, Huda Rosni, Wan Nurul Izzah, Nur Auni, and Danielin Alfon. Today, in high performance computing, the requirement to build supercomputers with higher processing power has resulted in the use of multi-threaded processors. Such system permits simultaneous operation of CPUs at considerably increase the execution speed. But one bottleneck in this architecture is the memory wall, which refers to the performance gap between fast processors and slow memory. For this cache memory is used for storing frequently used data near the memory, it can reach close to the processor. This project uses SMP Cache 2.0 Trace-Driven Simulator Cache Memory System on Symmetric Multiprocessors (SMP) architecture. This simulation enables the empirical investigation of various architectural parameters, for example, number of processors and cache sizes on the basic performance variation of the system. Now, we will enter the design pattern. Our design pattern is the template method pattern, which is a blueprint for an algorithm. It defines a fixed sequence as a step in base class, which allowing subclasses to fill in their specific details. The key benefit is DRY, do not repeat yourself, by centralizing common code to prevent duplication, developer velocity by speeding up work by providing a clear structure for extending system, and consistency that ensures the core process remain unchangeable across different implementations. Choosing the right architecture creates a high cognitive load, which is mental strain for developers. By that, design pattern act as mental schemes, which is a pre-built map that help organize complex information, bridging the cognitive gap, which is move the focus from minute implementation details to high-level logic, and also helps novice developers think more like experts by using proven structures. By that, faster problem solving and more robust, maintainable.
My name is Danielin Alphonse. Now I'm going to present about the simulation task for this project. For this project, we use SMP Cache 2.0 simulator to analyze cache performance for project 1 set in C using the SWM memory trace. First, we configure the system with a fully associative cache LRU replacement policy and the MESI coherence protocol. When we loaded the SWM memory trace and executed the simulation for 20,000 memory accesses. During the simulation, we observed cache hits, cache misses, hit rate, miss rate, and the cache evolution graphs. This is the result from the cache simulator, and we can see the hit misses rate of SWM, and we can see the SWM graph. For the cache hits, it's the second graph. The cache misses graph is the third graph, and the fifth graph is the hits rate graph, and misses rate graph is the last one. From the simulation results, we observed that the miss rate was initially high due to cold misses. However, the execution progressed, the miss rate decreased and stabilized. The final cache miss rate recorded for SWM was 19.63%, which corresponds to a high cache rate of around 80%. As the locality strengths, temporal locality successfully retained frequently accessed blocks via the LRU policy. Spatially locality benefits from accessing adjacent memory locations within the same block. Efficiency, the fully associative mapping maximizes the storage utility, allowing for moderate to good performance despite the workload's complexity.
Moving on to the result and discussion section, we have 3 tasks, and the first task is to obtain the miss rate using the memory traces SWM, UCOM, and WAVE. These traces were extracted from their perspective.prg files and show how efficiently the system handles memory requests under different workloads. Based on Table 1 and the bar chart shown, we can see clear differences in performance. The SWM trace recorded the highest miss rate at 90.63%. On the other hand, UCOM showed the best performance with the lowest miss rate at 17.27%. The wave stress falls between the two with a miss rate of 17.48%. When the data is presented in the graph, the difference becomes clearer. UCOM and WAVE have very similar miss rate with only a 0.21% difference between them. However, the SWM trace shows a noticeably higher miss rate exceeding the others by more than 2%.
Question number 2 is, two of the program have the same locality grade, which is the program with the best locality and which have the worst. Do you think that the design of memory system that exploit the locality of certain kind of program, which will be the most common in a system, can increase the system performance and why? So the answer is no. The program do not have the same locality grade. This can be observed directly from the differences in miss rate. The program that has the best locality is UCOM. UCOM records the lowest miss rate, which is 70.27%, which indicate that it has the best locality among the SETC program. A lower miss rate means data accessed by the processor is reused more effectively while still in the cache. SWM has the highest miss rate, which is 19.63%, which indicate the worst locality among the three programs. This suggests that SWM access a larger working set or replace cache block more frequently, leading to more cache misses. And yes, designing memory system that exploit the locality of commonly executed program can significantly increase system performance. When program have a good locality, cache hit rate improve, memory access latency is reduced, and processors spend less time waiting for the data from memory. This leading to faster execution and better overall system efficiency. Question number 3 is, during the development of the experiment, can you observe graphically how in general the miss rate decreases as the execution of program goes forward? Why? Explain the reason. So, during the execution of the experiment, it was also observed that the miss rate generally decreases as the program execution progresses. This behavior is mainly due to the presence of compulsory misses at the beginning of execution, when the cache is initially empty. As the program continues to run, frequently access data and instructions are loaded into the cache, causing the cache to gradually warm up. Once the cache contains the program working set, subsequent access are more likely to result in cache hits. Additionally, temporal and spatial locality further contribute the effect, as the program tends to reuse the same data and access nearby memory location repeatedly.
The simulation of the SETC SWM benchmark using SMP Cache 2.0 demonstrates strong cache efficiency, achieving a 19.63% miss rate by utilizing a fully associative cache and the MSEI protocol. The system successfully minimized conflict misses and maintained data consistency. While cold start misses were present initially, the results stabilized quickly, proving that the SWM workload benefits significantly from both temporal and spatial locality. Ultimately, the experiment confirms that high-performance multiprocessor computing relies on the synergy between optimized hardware configuration and software memory access patterns. That's all from us. Thank you for watching.